Okay, section 5.6, quadratic equations and complex numbers. Now take a look. We're going to classify and find all the roots of a quadratic equation. We're going to graph and perform operations on our complex system of numbers. If you keep in mind, we've been working with what we would call quadratic equations, and for the most part we've been able to solve them, but we've had a few instances where we would sort of get stuck and we would say, oh, there's not a solution. And in particular, it's been when we've had negative numbers underneath the square root. So if you look at the square root on some of our problems, we said the square root of negative 5 was part of our answer. And if we analyzed that and said, well, we're looking for that one number that multiplies by itself to give me a negative 5. Most people would say, well, wait a minute. I need a negative and a positive just to get a negative number. So that wouldn't fit the rule that says I need the same number. And we ran into a slight problem. So today we're going to take care of that, we hope, with a series of definitions and introduction to a new set of numbers called the imaginary numbers. So, when we've been dealing with our square numbers, and k was a positive number, we would take the square root of both sides. We would get k equals plus or minus that k value. And we would know we would have two solutions. Sometimes it ended up being a whole number, sometimes it ended up being a decimal, but with a positive number underneath that square root, we were definitely able to take the square root. But now, when we had x squared equals a negative number, and we took the square root, we ran into a few problems. So this is going to be the statement we're talking about today. The positive situation, done. We're good. Whether it's a whole number that's a perfect square or even not, we were able to solve that. But now, look at this one. X squared equals negative 64. If we followed our same steps and took the square root of both sides, we would be at x equals plus or minus the square root of negative 64. Now, the theory goes, as these brilliant mathematicians were working way back in time, and they kept getting this answer. They didn't want to have to deal with it. So the easiest thing was, hey, I could do that square root if I just got rid of that negative sign or factored it out. So what they started doing was saying we're going to have plus or minus, and then they thought of that square root as a negative 1 times that positive number that remained. So now they were able to finish the square root process with the thinking that, well, the square root of 64 can be broken down with the square root of negative 1 just being remaining. So then they had a plus or minus 8 with that square root of negative 1 always remaining. So after a while, these brilliant men finally said, you know, let's just give it a name. It is a number. It's a square root of a negative number, and it's always a negative 1 because they factored it out. And this is where the idea of the imaginary numbers came from. Okay? The imaginary number is a non-real number that can be written in the form of bi. Now, in order to work in the imaginary number system, you have to remember these two things. That I will be equal to the square root of negative 1. So in our statement over here, we could come back and say, that our final answer would be plus or minus, the square root of 64 would be 8, the square root of negative 1 would be the I that we just talked about. So we would have I, times the square root of 64, but we know the square root of 64 is 8, so when we finish, plus or minus 8i. And that would be our final answer for simplifying x equals plus or minus the square root of negative 64. And then if we squared this, first statement, you would get x squared equals negative 1. So if you want to be able to manipulate or move around or calculate in what we call the imaginary number system, something that they came up with basically as a way to still maneuver and work the problem out, but keep in that factor of square root of negative 1. So it's been named as I. I is a variable that's very rarely used, stayed away from, because it does mean square root of negative 1. Okay, so any number that is in the form of bi, which is what we have right here, anything that has that I characteristic in it, whether it's I squared or I, but really if it's I squared you should probably rename it as negative 1. And we're going to be practicing working with manipulating a few numbers with this imaginary stuff. So let's go to that. So the imaginary numbers go something like this. Names for the same thing. If I said, what is the solution to x squared equals negative 7? So most of you right there would start taking the square root of both sides. That's the same as, what are the square roots of negative 7? You think about what results. And then the expression, the square root of negative 7 and negative square root of 7. These are all names for the same thing. And then last but not least, the best choice, and that's why I have it starred, if you factor out that square root of negative 1 like we showed, then you will have I square root of 7 and negative I square roots of 7. So these are all names for the same thing, and just how you want to think of it as we work through them. So state whether the number is real or imaginary, and you can just write IMAG. So you could go through right away and say R or I for imaginary, but it always takes a little to do the calculation. So you want to think through these based on what we've done in the past. So here we go. First time through using imaginary numbers, how do you calculate with them? So a lot of the rules are exactly the same as the real numbers. So when you see squared and multiplying and adding, you're going to see plenty of similarities. So let's start at this first one. 8i squared. And we will state whether it's real or imaginary after we evaluate it. So 8i squared, most of you know that you could do 8i squared and rewrite it, or you could just square everything that's on the inside of the parentheses. If you do that, we'd have to multiply 8 times 8, and that's definitely 64, and I times I, which is I squared, just like a regular variable. And from there, I squared, based on our memorizing, means negative 1, so we'd be looking at 64 times the negative 1, multiply that out, our final answer is negative 64, and we definitely would say we are in the real number system for that one. Negative 64 is definitely a real number. All right, let's go to the next one. Negative 3 times the square root of negative 49. Negative 3 is a whole number out front. Let's analyze the square root of negative 49. Just like they did, which was we would take the whole number part times by the factor of negative 1. You would then separate it in your thinking or on paper, both, your choice, and you would evaluate. So from here, square root of 49 is 7, but we already have a whole number out front, so we're going to have to combine those two things. And then the square root of negative 1 we learned was I. So when we finish on this one, negative 3 times 7 is negative 21 times I, we get negative 21I. That is definitely an example of an imaginary number because it has that I component to it. All right, and our next one. When we have square roots, we must simplify those square roots first. So the square root of negative 9, let's see if we can jump without breaking it down this time, is the perfect square number of 9 with that square root of negative 1. So that would be 3i. Then the square root of negative 21, same thing. The 121 is a perfect square. We're going to multiply that by 11i. numbers times numbers, variables times variables, just like we always have, we would get 33i squared. I squared is better known as -1, based on our little memorizing that we talked about for imaginary numbers, and -1 times 33 is -33. So we definitely have a real number situation there. So you don't just look at what you have to begin with and say, oh, that's negative, that's a square root underneath. You have to actually go through and simplify each problem. All right. On this one, show that I square root of 7 is the square root of -7. Now, what we mean here, and let's just focus on one of these at a time. So, what we mean here is show that that number is the square root. If it's the square root, then that means we should be able to square it, and it should equal that -7. So that's probably our best plan of attack here. So let's take I radical 7. Let's go ahead and square it, and let's see, this is our question, if it really equals a -7. So again, just like we did a moment ago, when you square a number, you would square the part outside of the radical, and you would square the radical. So we're going to get I squared times square root of 7 times square root of 7. Some of you would say square root of 49. Others of you would say, well, that's just 7. And then from there, what does I squared equal to? -1. -1 times 7 gives you -7, and it truly does equal -7. So you have shown that it truly equals. And it is the square root of -7. Next one is just a quadratic equation. Some people say, well, shouldn't I use the quadratic on it? Well, notice that you do have a perfect square set equal to a number. And we solved plenty of these early on when we had just the positive versions. So if you can isolate the square, get the variable by itself, that would mean in this case, move that 100 to the other side, and get the square by itself. So we'll divide by 2 next. X squared equals -50. From there, you've learned you can take the square root of both sides. And since we're in a equation with a variable, we know we're going to get x equals plus or minus. Now, simplify that, square root. So you're looking at really the square root of 50 times that -1. Square root of 50, you should be able to simplify. That square root of -1 is your I value. If you can't do square root of 50 in your head, then start thinking about your perfect square numbers. What breaks down to give you 50? We want the biggest combination. So we should end up with the 50 will turn into 25 times 2. Think of it that way. And then that 25 is going to come out as a 5. The square root of 2 will still be there. So another name for the square root of 50 is 5 square roots of 2. And then we still have that -1 hanging around, and that square root of -1 we said was I. So the best way to write this so you don't have any confusion, and remember we said plus minus all the way through, x equals plus or minus the 5, the constant should go first, the I, which is a variable, is second because it's not underneath the square root, and then anything that you have that goes underneath the square root would go next. So our final answer is x equals plus or minus 5i root 2. Now, one step further. If we have the imaginary numbers, which take on the form of bi, we could go one step further and talk about the biggest number system we currently know about, and that is the complex numbers. By definition, we can say a complex number is a number of the form a plus bi. So here's the bi we were just talking about, where a and b are real numbers, and the I equals the square root of -1. The a is a real part, and b is the imaginary part. Two complex numbers are equal if a plus bi equals c plus di, which means their real parts are going to have to be equivalent values, and their imaginary parts are going to have to be equivalent values. We didn't say necessarily the exact same form, but equivalent values. And then the last thing to remember is when we're working in the complex numbers is that you can perform all your real number postulates, rules, properties on complex numbers except inequalities. So you can't use any of the inequality rules on your complex numbers. So with that, let's go ahead and try a few examples of what happens in the complex numbers. Now again, let's just shade this so that we can do one at a time, or at least only see two in this case. So if you look at what I have here, I'm looking at 6 minus 5i, which is a complex number, added to 3 plus 4i, which is also a complex number. So the rule in the complex numbers is to add the real part plus real part and the imaginary plus the imaginary. So it's sort of like collecting like terms. Think of it that way. So 6 plus 3 is 9. A negative 5i plus 4i is negative 1i. If you don't like writing your ones, you could get away with, and that would be in the form of a plus bi. It is a complex number. So we added two complex numbers and we got a complex. Over here we're subtracting. Subtracting is very similar, as you know, just like it is in addition. So again, the same thing. The real plus the real, but we're subtracting this time, so make it the real minus the real. So 2 take away 7 is negative 5, and then do the imaginary parts. I subtract a negative 2i minus a negative is plus a positive, so 1i plus 2i is 3i. And again, you have an answer that's really sitting here in a plus bi form, which is our complex number form. You don't have to put parentheses back around it to group it. It's just sometimes easier to see that as a complex number with those. So we added complex numbers, we subtracted complex numbers. Now let's try to do a little multiplication. The multiplication here, notice though, this is not a complex, that's an imaginary, times by a complex. So it should look a lot like something you've already done, like a monomial times a binomial. And what'd you do there? Distribute. So that's all we need to do here to finish this. Collect like terms when we're finished, and we should be good. So ready? 3i times 12i. The number times the number, 36i, just like variables in the past. And then 3i times a negative 3i would be negative 9i squared. You don't want to leave that because you should be seeing that you have some simplifying to do. Right here, the key is you have an I squared, and we have an easier form for I squared. So if we left 36i, because we can't do anything with that, minus 9i squared is negative 1. So a negative 9 times the negative 1 is a positive. And then if we put it back in a plus bi form, the 9 would lead off, and we'd have our plus 36i. So when we multiplied a complex times a monomial, we ended up with a complex. Our last and final one, let's over here, let's change colors this time because we got a lot of red going on. We have a complex times a complex. It should look really familiar to you, even with some things we've just been studying, in that we have a binomial times a binomial. Think of it that way. Even though we're looking at two complex numbers, binomial times a binomial. So FOIL is our right-hand man here. So here we go. We will FOIL and then simplify. First times first, 10. Outsides would give us negative 35i. Inside times inside would give us 18i. Last times last gives us negative 63i squared. So look at what you have. I see some i's right here in the middle, so we're going to underline those as they definitely need to be combined. And then on the end again, you're focusing on I squared equals a negative 1. So negative 63 times negative 1 would be a plus 63. So if we had that, we now have something we can combine with that 10 up front that was a nice whole number. So let's try to collect like terms and write this in complex number form right from the beginning. So we need our a value, which is our constants. So 10 and 63 is 73. Plus our constants, we've got a negative 35 and an 18. That should leave us with a negative 17i. So you could either write it as 73 plus a negative like we did, or even the 73 minus 17i. Both of those would be acceptable. So we've added, subtracted, multiplied in two different ways with our complex numbers. Last but not least, let's talk about a characteristic here. This is another multiplication one, but a little easier. The numbers are small, so here we go in FOIL. First times first, 1. Outsides, we get a negative 1i. Insides, we get a positive 1i. And last times last, we get a negative I squared. Now before we go any further, look at what we were actually multiplying. Besides just saying it was like two binomials, the parentheses were exactly alike, item for item, with the exception of one was plus, one was minus. It sort of looks like our difference of squares factors if you think about it. So now let's clean this up and see what type of answer we do get. We have our 1. Combined like terms in the middle here. Looks like we're going to cancel, and those would eliminate. And then last but not least, when we take a negative I squared, since I squared equals negative 1, that would be negative 1 times a negative, so plus 1. And that would give us an answer of 2. This is huge. This is a complex set of numbers being multiplied together to give us a real number. Now let's see what we've got hidden here. Every real number is complex because a plus 0i is how you would write it. So if I said my number is 5, write it as a complex number, you're just thinking 5 plus 0i. Every real number can be written that way. Does that mean from here on out that's how we're going to have to write our real numbers? No. But in the back of your mind you're saying the number 5 really is complex. It just has a 0 imaginary part. The other one, whoops. This combination of complex numbers that we just used up here is called the complex conjugate. And it will be a big piece, a big part of our multiplying in division. That's the only process you'll notice we haven't done yet. So complex conjugates are going to come in handy because they were the ones that allowed us to start with two complex numbers but get to a real number when we finished. So let's go ahead and look at that division step and we'll be done. So here's 2, and if you look at this, if they're both complex numbers, which is what our numerator is and our denominator, the rule is similar to radicals. You should not have radicals in the denominator. You should not have complex numbers in your denominator. So if we can't have complex numbers, we have to use that little trick we just learned to get rid of a complex number. The only way we really can do it is to use its complex conjugate. So that's what we're going to multiply both the numerator and the denominator by. Now remember, the complex conjugate was the exact same form except for the sign was opposite. So our real number is a negative 2. Our imaginary part is a 5i. Our sign will have to be a plus. And we're going to multiply that on both the top and the bottom. Now when you say, well, why? Because it's just the denominator you said you wanted to get rid of. But remember, in math, you've got that fancy form of 1. That's all that is, if you look at it. Anything divided by itself is 1. So if we've got a fancy form of 1 there, we're not really changing our problem when we multiply. Now, granted, we will be changing the look of it, but we didn't do anything so that we would change the problem from its original. So if we get rid of our fancy form of 1 here, and actually now multiply by the negative 2 plus 5i, we should be able to get some solutions or a better form of this fraction division. The number one rule is start with the denominator, because if you do not get that real number, something's wrong. So I'm going to say I'm going to work on my denominator first, so everything down below, it looks like FOIL again, so first times first, 4. Outsides would be a negative 10i. Insides would be a positive 10i. And last times last would be a negative 25i squared. Simplify, you can see your two middle terms will cancel. The negative 25i squared is really positive 25. With the 4, our denominator ends up being 29. That's exactly what we wanted, a real number, not a complex number. So now we can go back and simplify up top. So first times first, negative 8. Outsides, 20i. Insides, negative 2i. Last times last, 5i squared. Now clean that up. Like terms, looks like we have 18i using the two middle terms. And with the 5i squared, which is really a negative 5, negative 5 plus the negative 8 is 13, and it's still negative. So we get negative 13 plus 18i. And if it says, like ours does, write your answer in a plus bi form, that really means we need to separate this, and our real number part is now this fraction, and our complex number part is also looking like a fraction. But fractions are okay as long as our denominator is a nice real number. Okay, so that leaves one more to do, and I want you guys to do that, and that can be our go-to problem and talk to what's going to happen on this one, because I really have, if you look at it, a complex number on top and an imaginary on the bottom. But follow the same rule we were talking about. What about your complex conjugate to get rid of it? Because this is not a good division problem, because you are currently housing an imaginary number in the denominator. So go ahead and divide that one out, give it your best shot based on what we just showed you, and we will discuss that one in class. So you've just learned today a quick look at how you're going to solve those negative square roots. You're going to use imaginary numbers, and then imaginary numbers really come from the bigger set of numbers called complex. So bring all your questions on these to class and get those two little facts memorized, that I equals the square root of negative 1 and I squared equals the whole number negative 1.